All right, so let me start. I was gonna go blasting on to the next topic, but I think it might be a good idea to me to run through briefly a little bit about this hard problem, because I'll be able to refer back to this if all goes well. So this is the if you can see that, yeah. This is the irreversible adiabatic compression of this ideal gas and how to do that problem. So the hard thing about it, which is not shared by the much easier isothermal one, is that when we compress the gas, be it reversibly or irreversibly, the final temperature changes, right? Because there's no heat in. All the work we do is deposited as internal energy, and that raises the temperature. And if we do different work, we get different temperatures. So we don't know the final temperature, and we don't know the pressure, the pressure we need to apply. We need to know the pressure we need to apply because we have a target. We need to hit half of V naught as the final volume. Okay, so we don't know enough to do the problem. So, but we have math at our disposal, right? Math is the great tool we use to solve such problems, be it in this class or in finance or wherever. So what we need is we need two equations and two unknowns. The two unknowns are the final temperature and that external pressure, okay? And the external pressure is going to be the final pressure, right? Because remember what happens, we apply this pressure, the forces are out of balance, and once we get to the end, then we stop because the internal and external pressures match. So we need to know all that, okay? So here's how I decided to do it, okay? So we need to, let me get my, there's some sort of mode here. I'm trying to be fancy, but I'm going to give up. There's some, I can't find a laser pointer. You think they, I'll start erasing things if I go wrong. I'll do a little highlighting. Okay, so we need to find expressions involving P external, and I should say and T final, and then solve them. So we know, because it's adiabatic, the final energy is going to be the initial energy plus the work we do. We're going to do positive work, and so 3 halves RTF equals 3 halves RT naught minus PXT delta V. Remember, delta V is negative. It's minus V naught over 2. So that second term is positive. And we can go through that. So I can solve. I have the final temperature as a function of things I know and the external pressure, right? So there's one equation and two unknowns, and I'm trying to have good lab technique. So I'm going to get another independent equation, and I'm going to write that as TF equals something, and then I'm going to set them equal to each other, and then I'll have only one equation that involves the external pressure, because that's the one I really care about. So what else do we have? We used we used one of the equations of state, like U is 3 halves RT. We use that one here, and we use the first law, okay, conservation of energy. Now I'm going to use the ideal gas law, PV equals RT. And so PFVF equals RTF. And there's that TF I'm trying to get. And so I can arrange that. My VF is V naught over 2, right? That's the final volume. So I can get TF equals P external V naught over 2R. So there I have what I want. And I set them equal to each other. Actually, I didn't set them equal to each other. I solved them. But when you solve that, and did I make a mistake? I'll check myself at the end, but I still could have made a mistake. It's possible. But what I find is something that makes sense, I guess, that my initial pressure, my external pressure has to be 6 times the initial pressure if I'm going to compress the gas to that half volume. Remember, for the isothermal one, it was twice the final. The external pressure was twice the initial pressure, because that would get me to half of the volume if the temperature didn't change. The temperature's changing now, so the gas is less happy, and I've got to really, I can force this with 6, okay? And if I go through and I calculate the work now, I can put that in, minus P external delta V, and I get, so the work is 3 RT naught. And the work I did before for the reversible adiabatic one, if I go back and check that, because they're in here too, was a 3/2 RT naught, 2 to the 2/3 minus 1. So a different answer if I do it reversibly. In a way, this one's easier because the integral's easier, right? That's why you don't get weird numbers, because you're not doing this 1 over x to the 5/3 integral. But you needed to do that thinking to get the external pressure. So my delta U is equal to the work 3 T naught, and so my final temperature is 3 T naught. So I go through this calculations. 3/2 RT naught plus. So I substitute that in, and I can find the final. U sub final is 3/2 RT sub final, and so if delta U is 3 RT naught, I can find my final energy, which is 3/2 RT naught plus 3 RT naught, which is 9/2 RT naught, which is 3/2 RT final, which is the final temperature is 3 times what it was initially. And we can go back and see what it was for the reversible one, probably. It was 2 to the 2/3 what it was initially. So it's a significant difference, right? I mean, and now, did I make a mistake? Maybe I did. Please tell me if I did. But at least I can check something, okay? So, PV over RT for 1 mole, it should be equal to 1, right? Which means that, P final V final over T final should be equal to P naught V naught over T naught. And if I put in 6 P naught for P final, V naught over 2 for V final, and R times 3 T naught's T final, indeed, it equals P naught V naught over RT naught. So if I did screw it up somehow, it's a more subtle thing that I did, and it's still compliant with this kind of logic. Okay, so that's I didn't want to waste too much time. Well, I do like to waste time, but I didn't want to waste too much time on that. So now, unless there's a compelling question, we'll move on. Okay, we're flying through the material, and we're into the third focus. And this is where things get, this is where we really can talk about what it's all about, because we get to the second commandment of the 3 commandments of thermodynamics, which is the second law of thermodynamics. And what this it tells us, second law. I like the second law a lot, I have to say. And, I play the guitar, and I play in a rock band. Guess what the name of the band is? Second law. Yeah, we have a Halloween gig on the 29th. So anyway, the tips, they don't pay me as much as the being a faculty member, but I tell you, the tips are better. So, there's advantages and disadvantages to all pastimes. So the second law, it tells us what will happen spontaneously. So some things happen, some things don't, and some things just happen spontaneously, and we'll see what the second law has to say about that. think I could do better organization here. Okay. Bullet point tells us what will happen spontaneously. It precisely defines what we mean by reversible. So we have this, we've been talking about reversible things. The forces are a little, you have to balance the forces and this and that. So we have this idea that everything is sort of balanced, right, and it happens really slowly. The second law will give us the definition that I would be fishing for, most likely if I do fish for definitions, of what it means to be reversible. And laws come into your life when they prevent you from doing something. I can't smoke this, I can't drink that, I can't buy that, I can't go this fast, right? And so the second law also tells us what is not allowed. That's why it's a law, I guess. And you're okay. So there we go. Your book talks about a couple historical figures and what they have to say about it. And we'll name drop this guy Clausius. I have a shock story about Clausius. Should I tell it? Okay. So, we're all assistant professors, right? I'm pretty young, and I'm talking to a friend of mine who's also assistant professor, who also plays the guitar, in fact. He had the same, he was older, right? He spent a few years out of academics, and he had a band in Texas with the same promoter that ZZ Top had. So he was traveling around Texas. So we're chatting, and Professor Shaka walks up, and he has a look of disdain on his face. He goes, I just met somebody who didn't know what the Clausius-Clapeyron equation is. Okay. And you can imagine, like, he was more arrogant back then. He's mellowed out a lot. And so, he sits down with his coffee, and I look over at Pat, and he looks at me. And it's clear that neither of us remember which equation that is, because we haven't been teaching Chem in recent times. So anyway, that's enough of the story. But this Clausius, he basically says, and the words are in your book, so this is, he will do that if I have a hot thing, right? T sub H is hot and cold. That's okay. But this, no, that can't happen. Heat does not flow from cold to hot. That's what he said. And you might say, this is obvious, but it's a very interesting history of thermodynamics and how people figured out all these things. But just in physics in general, like Newton, Newton came up with Newton's three laws. And obviously, the energy of the system has to be conserved. That's what we would say in physics class. Well, they didn't know about energy. They didn't have this idea. It's just like you look up in the sky and stuff's doing its dance, and it's a circle or it's an ellipse. So this came out of it. What people didn't know, but still figured stuff out. So this is sort of in that spirit. Now, so that's pretty obvious. What we more useful to us, and we'll talk about this idea in detail, and perhaps Iwan Andrei. So we'll have a question on our first midterm. Spell Iwan's last name. And it's sort of like his family probably did this happen. No, he's from Romania. He's Romanian, and not only that. Okay, I should warn you. He's not just from Romania. He's from a part of Romania that is particularly famous in lore. So what is the most infamous part of Romania? Transylvania, okay? So I've never actually seen him in sunlight. And so if you go to, if he has office hours or something, wear some garlic around your neck, okay? So I've given him a hard time about that over the years. But anyway, somehow he went through some kind of semi-permeable membrane, which removed almost all the consonants from his name. There's just a lot of vowels. Anyway, don't tell him I said that, because he's doing me a favor. But here's another. This is Kelvin. He got something named after him. He was a lord too, Lord Kelvin. And so we have this idea of hot and cold, and we can, we can be like those engineers which I've warned you about. If an engineer has a steam engine with boiling water in it, then it's just natural to want to make the thing go, right? So they're gonna somehow use the fact that it's hot, and the environment is not. So like T sub H is a steam engine. T sub C is the outside world, the surroundings, and because you have a thermal difference, we can do something useful. That is quite true. So you might stick an engine in here, and then we can let nature do its thing. And so I'm drawing like a river here, and we'll call it Q sub H. So that's heat. Flowing out of the hot thing into the river. And what we want to do is we want to get some work out. So work sub out is the engineer's work, and we want some positive work. And this is a river. It's a river of energy flowing, and the widths of the river obey the first law. So if I have a broad river, usually rivers don't split, but they come together, don't they? But if you can have a broad river and it can split into two rivers, and the two rivers they can't be as wide as the original river, and they somehow the water flowing has to conserve the fluid flow, right? So I can take some work out, and then I can also have some heat going into the cold reservoir. And the first law, we'll talk about this, is that Q sub H is QC plus work out. And the way I've drawn this is everything's positive, okay? So don't freak out about the signs, because the signs are what get you. So we're doing the engine. Actually, this is meant for the business majors, which don't really like negative numbers, because that means the company's gonna fail. They're gonna have to find another job, right? So everything is positive here. But the flow out is going to split into two pieces, and that's the first law of thermodynamics. But what Kelvin said, so this is okay. But what Kelvin said is we can't do this. You can't just, this is hot, by the way. You can't just take all of the energy in a hot thing and to convert it to work. And we'll talk about this is the second law. You always have to pay some tax. Let's say this is the tax, right? You have to give the angel's share. Like I was in a bar in Cuba, and they open a bottle of whatever the rum is, and they go like this. They throw some on the floor of the bar. Right, so I don't think communism has eradicated sort of folk, whatever you want to call it. This is for the angels, right? And there's some that has to be for the angels here, and we'll see that's what makes the second law of thermodynamics obeyed. And so this I should let me finish my. That's no good. I don't want you to get the wrong idea when you go back and look at these notes. Let's write a patent for that thing. All right. So we have a new idea, a new concept. We have the entropy, and it's S. Okay, and this quantifies these ideas. And entropy is a fascinating topic. There are still people that argue about whether is entropy a physical quantity like volume and pressure and energy, or is it a measure of what we know. You know, so is it sort of is it a mental thing? Because, you know, if we knew everything about every particle doing you know, like the world would be this deterministic, like a machine, right? These people, the physicists would argue about free will. Like when Newton came along, all we need to know are the initial conditions, and we just solved Newton's equations. And the Pope didn't like that, I don't think. You know, things like that would happen. But still, entropy is still kind of a fascinating thing. But we don't have time to talk about that. So I can define it like this. So this is a definition. And what this is an exact differential. Okay? So now I said dq is not an exact differential, and you know, life's too short to get it, especially for chemistry majors, right? To get into the weeds about what that means mathematically. We sort of talked about, you got to be careful with. It's not like the state functions, you know. But if I multiply, and this is the mathematician, this would satisfy the mathematician. If you multiply dq by an integrating factor, did you ever have those come up in the differential equations class? Multiply it by an integrating factor, then you can solve it. So if you multiply by 1 over t, and then we take dq sub rev, this is the reversible heat. Okay? And so an example of this, and we'll come back to this, when I took the isothermal ideal gas and I compressed it reversibly, right, I did work on the gas, right, but the temperature didn't change. So all the work I did on the gas left the gas as heat, right? So the reversible heat there was like Q, which was, remember, Q was negative for the compression. That negative value was the reversible heat for that example. And so if I want to get delta S, right, I can integrate from like A to B, dq reversible over T, and T could be changing, right? And that's what I get, and I could write that as SB minus SA, because S is like the other things we've met, a subset of them is a state function. So like S is a function of T and V, for instance. It only depends on the T and the V. It doesn't depend on the path. And so if I was going to draw a picture that looks like this, T and V, and I might have some surface like this, and I'm trying to draw it accurately here, it's only half accurate. I'm being destructive, right? I'm destroying my own. So it's going up, like, you might just guess before you even showed up here that if the temperature goes up, the entropy is probably going to go up, right? So I wanted to draw it complying with that. So we have a surface T and V, and I have point A and I have point B, and there's like this is path 1, and let's say path 2. And if I want delta S is SB minus SA, find a reversible path and integrate, and then we'll have delta S equals the integral from A to B dq reversible over T. Okay, and you know we've sort of done that. There's an example which I'll go through. We've already done both of those cases, which I do have time to talk about, which I'll do now. So this is sort of an abstract picture, but I hope that idea is okay. So let's go back to our friend, not Professor Shaka, our other friend, which is the isothermal gas. So for the isothermal gas compression, we did this, and we had V. V equals V naught going to V equals 1/2 V naught. T naught is constant. And the work was, R T naught log of 2, right? So that's the problem we did. But let's do it in general. So in general, so we that was a problem. We gave I gave you a specific example. But let's say I have n moles, an initial volume and a final volume, and we're just going to let n be whatever and V final be whatever. And if we go back and we did that calculation, we would find, let's do our full accounting, right? So T is constant, and delta U is 0, right? Because it's isothermal. That'll be one of the questions on an exam, which is equal to Q plus W. W was the first thing we did. We got minus nRT log V final over V naught. And this one was up here. I wrote it was RT naught log 2, right? But there was a minus out front, and V final over V naught was 1/2. So this is the general. There's a minus in front from minus PDV. So that's the work in general, right? And I'll put T naught in that because we're doing this isothermal. That is fixed. I mean, if we did adiabatic, it'd be a different formula. So I'm not going to let that T be running around as a variable. The Q is plus nRT naught log V final over V naught. And we can get delta H, and this is actually a problem. So let me just remind you, right? You're doing this problem now, so here's a spoiler. So H is U plus PV, right? That was a definition. It's like defined as, but that's equal to, let's say, 3. 3/2, I'm going to put the N in, nRT plus nRT for the ideal gas, because PV equals nRT. And so, H is a function of T and V, but it's equal to 5/2 nRT for the ideal gas. Monoatomic. So it's confusing. That 5/2 is a coincidence, right? Because that would be U for the diatomic, but for the monoatomic, U is 3/2. But I've added RT to it. And so H is a function of only temperature. For the ideal gas, not only does U only depend on temperature, but H only depends on temperature. If it was the van der Waals, then you'd have some mess, right? You already saw in the first week that. You didn't see the H, I don't think, but it's there and you could calculate it. And if I was mean, that's what the exam would be all about, right? But how do you know? Maybe I'm just pretending like I'm not mean. You'll find out on the 30th. Anyway, what is delta H then for that process? It's 0, right? For isothermal compression, or just any isothermal volume change. That's the problem we're doing. So what is delta S? That's the new thing we're adding. See, the list of the laundry list keeps getting longer. And that's the integral from V naught to V final of dq reversible over T naught, because the T is not changing. And if I could take the T naught out, and then I'll just get, I can call it Q reversible. So, but I'm doing this problem, I'm doing reversibly, right? Yes. Yes. Okay. Yes. That's exactly. So what I did, when you do this problem, it was just a problem to do, but this happens to be a reversible path from the initial state to the final state, right? And the temperature doesn't change, the pressure's twice as, I mean, for the one I gave you, twice as big, and the volume is half as big, right? So, but in general, I can use this because this is reversible. Now, it isn't always, and when I did, in fact, when I did the problem with the constant pressure, I got a bigger, I got a more, well, it was compression, right? I got a more negative Q, didn't I? Right? That's because I had a path from the same initial to the same final. That one wasn't reversible, okay? And I cannot use that Q to talk about the system, okay? And so what I find is the delta S for this is NR log V final over V initial. And for the compression problem, if V final is less than V initial, so like for any compression, but in particular you did a compression problem, and intuitively you say, well, entropy. I know what entropy is. I don't need to take P-Chem. I know that if I heat it up, the entropy is going to, if it gets hotter, higher temperature, the entropy is going to go up. And if I know if I take it and cram it into a smaller space, I'm going to it's like cats in one room instead of in the whole apartment, the entropy is going to go down, right? And so if the temperature stayed the same but the volume got smaller, you're going to say to yourself, I think the entropy went down. But you feel uncomfortable about it because there's sort of the second law lurking around. But for compression, delta S is negative. Okay, it is negative. I mean, it's okay. It's okay. You can get negative changes in entropy, as long as you're not talking about everything, right? And so for that problem, for compression, delta S is negative. But what if the final volume is bigger than the initial volume? Then what is a sign of? I could ask questions like this without doing any math. The volume goes from V naught to 2V naught. What happens at constant temperature? What happens to the entropy? Does it go up, go down, or stay the same? It goes up, right? That makes sense, I hope. And so, but the going down. So I have delta S is equal to NR log V final over V initial. And this is because I've found a reversible path. Now, there's a delta S of the surroundings. So if I draw my picture, here's the surroundings. I've got my piston, right? And I'm compressing it, and heat goes like that, Q, right? So delta S of the surroundings is going to be Q of the surroundings divided by the temperature, and the temperature of the surroundings is T naught. Like if you were doing nanotechnology or something like that, okay, and you have some molecular system, and your computer will have on it like a heat sink or something like this, something that just picks up heat. And if it's really small, then you might put heat into some surrounding, and the temperature of the surrounding might go up. But it's like the ocean, right? The problem when I threw the hot block in the ocean, the surroundings heat capacity, I'll get you in a second. The sea of the surroundings goes to infinity, right? The heat capacity of the surroundings. So I could put however much heat in the surroundings, and its temperature is not going to change. So that would be how I would do the bookkeeping for the heat that goes in the surroundings. And of course, this is going to be minus the Q of the system over T naught. So delta S of the surroundings. And I should say the obvious, like Q of the surroundings is equal to minus the Q of the system, which I better not call system Q. I mean, that is just what happens when you put the arrows on the other end of a vector, right? The heat flow from the system's perspective is Q, but if I now say I'm the surroundings, then it's the same quantity but with a minus sign. You had a question? Well, yeah. So that's what we're going to find. Okay. So for this reversible process, this is for the reversible one, right? Because that's the problem we're doing. We find that it's equal to minus nr log v final over v initial. So it's a negative. And so what really matters, though, and I think I told you this already. There's delta S of the universe, and in my limited, like I've lived in this small town all my life, so the universe to me is only the system plus the surroundings, and so that's going to be nr log v final over v initial minus nr log v final over v initial, and that's equal to 0, okay? And so this is our precise definition. If something is reversible, and in this example it was reversible, and we happen to find for this one example, delta S of the universe equals 0. But this is generally true. So if I have another reversible process, and I calculate delta S for that other reversible process, I am going to get 0 for the universe, okay? And let's just think here for a second, because we've only done a few problems, but they really explain everything. That's why it's useful to just chew on these problems, like one of the Nebraska cows, chewing its cud, because you get more and more nutrition out of it. Isn't that a disgusting metaphor? But anyway, not as bad as thermodynamics, you're thinking to yourself. But anyway, so let's think about the reversible adiabatic compression that I did for the gas. Remember that integral of x over 1 over x to the 5 thirds? I calculated a work. I calculated a delta V. I calculated a change in temperature. What was the heat? What was Q for the adiabatic one? Okay. Did any heat go into the surroundings? No. So what was delta S of the gas that I compressed adiabatically and reversibly? What was delta S for that gas? Well, I mean, the temperature went up, so that's working to make delta S positive. The volume went down, that's working to make delta S negative. But what I know, no heat flowed, and I found a reversible path to compress the gas, and dq was 0 for every step of that. So what do you think delta S by its definition would be for that gas? 0. So if I compress the gas adiabatically and reversibly, delta S is 0 just of the gas, and the counter the tug of war between temperature and volume, wanting to make the entropy go up or down, exactly balances for that one. But now, let's think further. I did it irreversibly. What was Q for the irreversible adiabatic compression? 0. So did the surroundings entropy change? No. Irreversible, but the gas is hotter, okay? So you might just think intuitively, I've got a tug of war between volume, right? Volume shrinking is going to want to make the entropy go down. Temperature going up is going to make the entropy go up. For the reversible one, the temperature didn't go up that much, and it was just balanced. But now your big roommate who's on the water polo team, right? We don't have a football team, so that's the next best thing. Right, a water polo goalie. They can shred water like mad. Both my kids played water polo, so I never figured out the rules. Too complicated for me. But now the temperature goes up, and so there's a new person in the tug of war. And so which one wins? The temperature one, because it went up more. And so what do you think happens to the entropy of the irreversible? The irreversible delta S of the gas, adiabatic. Positive. Okay. We said, well, maybe delta S is negative. We'll see about that, right? Because for that problem, because there's no heat going to the surroundings, delta S of the universe is simply delta S of the gas. Yeah. Well, yeah, in some sense, in the precise sense of their compensating factors in the entropy. Right. Because you know S is a function of T and V. I mean, you could say, okay, S is a function of T and V, right? And I went T final, V final here, right? And so S is a function of T final, V final equals S of T naught, V naught for the reversible one, right? But for the irreversible one, the T final's higher, but we kept the V final the same. And if entropy goes up with temperature, it just is this obvious? It is if you're well practiced in thinking about turning physical problems into mathematical equations, which you aren't, okay? But maybe someday. But what I'm saying is that it's plausible, I hope at least, that if you raise the temperature, the entropy will be different then, and delta S will be positive. We can calculate it. Do we want to? Oh, where's the guy that said no last time? Let's see. But no, let's do the irreversible. Let's do this one. Irreversible isothermal. Right, and so remember that one. Our work was minus Pxt delta V, which was equal to P naught, 2P naught, V naught over 2, which is P naught V naught, which is RT naught. So instead of being RT naught log 2, and so I'm doing the n equals 1 case because the other one was I could have a general formula, but now like every one of these irreversible ones is like specific. So I'm going to stick to the one that you did in the homework. Yeah. Which one? So work is minus P external delta V, then 2 P naught. Because remember that I'm assuming perhaps not a good assumption that you're remembering when you had that external pressure to take you to half the volume had to be twice the initial pressure, right? So that's the work, and before it was RT naught log 2, right? So we had 0.693 of RT naught instead of 1.0 times RT naught. So for the reversible one, we did less work. Now, delta U is equal to 0 because the T is still constant. And what is delta S? How are we going to find delta S for this irreversible compression from V naught T naught to V naught over 2 T naught. So what is the definition of the entropy, ds? It's, you know, dq reversible over t. So I need to find a reversible path that gets from here to there, to the, you know, the same change of the system part, just the gas. Well, I just did that, didn't I? Right? I did that already, and so delta S is going to be R log, let's say R log, you know, V final over V naught, which is minus NR log 2. That's what that's the general formula. NR, let me get rid of that R. Okay, so the general formula we had was NR log V final over V naught. We saw that just a bit ago. And then for this problem, it's minus R log 2, which is R log 1/2, right? The 1/2 log minus log 2. So even I didn't do it reversibly. I did not do this process reversibly. But to calculate the entropy change of the system, I found a reversible path and did it that way. Why can I do that? Because it's a state function. It doesn't depend on the path. So I've used a trick. I used a loophole, okay? And I was able to calculate that delta S. I'll be done in just a couple minutes, because there's a punchline, right? So my Q, though, was minus work, which was minus R T naught, delta S of the surroundings. Okay, to do the surroundings, you don't find a reversible path, okay? I dumped, you know, like if I have surroundings and I dump a certain amount of heat in it, it's going to raise, if I put heat in the surroundings, its entropy is going to go up. It doesn't matter how I did it. So now to do the surroundings part, I use what I actually did here, okay? So that's going to be Q the surroundings divided by T naught, which is minus, I should put you know, Q surroundings. Well, I could just say it's minus W over T naught. Wait, actually, I'm getting too many minuses. Let me just be a little clear here. So, you know, Q was minus R T naught. So that Q is the heat that left the system, right? It left the system. And so the surroundings, Q is just a minus of that. So I have R T naught divided by T naught, so it's equal to R. Okay, so delta S of the universe, here's the punchline.